So this video's on making Python fast, and it's actually born out of the fact that I was doing that little project on, where is it there? Over here, where I was kind of like testing Pygame, and I was doing a simulation for an n-body simulation for galaxy mergers that basically takes a lot of computational power, and it was beginning to get slow. And people say that Python is slow, and in fact, not only is it slow, but from all of the languages, it's one of the slowest. But actually, that's because, generally speaking, users might not be using it in the right way to enhance its features and actually to bring it right up to some of the fastest languages. Now, in order to know this, we basically have to remember that Python is built, or at least our version of Python, for like 90% of the Pythons are out there, are what's known as C Python. So they're built, so Python's built on top of the C library, the C language, as is C++. So kind of like in a different way. One's a structured version, one's a dynamic version. Python's a dynamic version. But generally speaking, Python offers you a lot of flexibility. And that's why it appears to be slower. But it also offers users the opportunity, if they want to give up this flexibility, where they want to have power or speed in their code, that they could actually do this too. So here's like the classic example, which is if I make a list in Python. So for I just want to make, I guess I'll just make a list. I'm just thinking the best way of doing this. X equals, and then we'll create just some very big list. So n in x equals, okay, we're doing it, yeah, y for y in range, and then something reasonably large but not too large to start with, like 1,000. And then so we've created this list here. We just made a list. And we made a list using list comprehension. We didn't have to do this. We could have done it in the classical way, which is with a for loop. For I in range, we could have declared this empty list at x equals null. The list comprehension produces exactly the same result, so I'll go to that, but I believe it's about 25% faster. So this is good, but it's just a convenient way of Python. And this is one of the conveniences that Python gives you, and you can do a one-liner and create this list quite fast. And actually, we can even print the list. So print x just to see what the list looks like, and we'll just get this list of 1,000 items. There we go. There's our 1,000 items, which we can scroll through down at the bottom. So we've created this list, and then we might want to do something like square all of the items in the list. And we could, again, do something like for I in range, but not even range, because this is now an iterable. I'll actually call this like our list or something like that. So our list. This is an iterable. We could still have our list here. That's what we do, but we're going to comment this out because we don't want it writing the big list every time. So for I in range, our list, and this is the convenience that Python offers you. Let's just go and we'll create another list, and we'll append, we'll just get the squares of all of those numbers. So we'll say squared list is equal to, and then we'll just assign it this blank list. And for I, find our list, we would just do squared list dot append, and then I squared. So something just like this, and there's nothing wrong with this. We could also put this into a list comprehension to make it a little bit faster, so we don't need to have the append and so forth. So we could do it again, something like I for I in, and then our list. So it'd be I squared for I in our list. And that's a little bit faster. So now we've got a classic way of doing it. We've got a classical for loop here, which iterates over our iterable. In our case, the iterable is our list, but we can also do a list comprehension. Both are good. We could even move our classical for loop to look like this, so it's all on one line, and effectively these two things are the same, this one and this one. But anyway, I'm going to remove the classical for loop. We don't actually really need this in our case for the purpose of the example. We've now got a list, and what we've done is for each item in our list, we've just got the square value for it. So we could do print just to verify the squared list. And that's what we will have done, and we can hit F5 and run our code. And observe the amount of time. Well, we get our squared numbers to start with, and then we could observe the amount of time it takes. And if I zoom through it, we can see from the top lines you've got 0, 1, 4, 9, 16. They're all the squared numbers that we recognise: 100, 121, 144, 12 squared, 13 squared, and so forth. So we've got that. Now, I should probably use a time it function, but I'm just going to use the regular time function. So import time. And then just before we start squaring over here, using our list comprehension, and I'm telling you that list comprehension is a little bit faster than the classical for loop, but either way, they're Python conveniences and they should be, or theoretically, slower than other methods potentially, or at least we're complaining, or the complaint is that Python is slow. So we can do t0, our starting time equals time dot time. And then afterwards, after we run this, we can do t1 equals time dot time. That will do a timer, and then we could print. We could also print our squared list. We don't need to print it because we know that the computation's done now. We've verified that it works. So we'll just comment that out for now. And what we can do is print something like time taken, and then t1 minus t0 seconds. We'll round this off to a couple of decimal places just for cleanliness. So round is number, and we'll round it off to say, I don't know, 3 decimal places. That should kind of like be sufficient for a crude example. And let's just run this again. But what this is going to do is going to give us a measure of how long it takes to square the list. So run that. And you see it takes 0 seconds over there. So we can now start forcing our list potentially to be a bit bigger. So let's just add a couple of zeros on there. And again, run our code. Probably still take 0, or maybe close to 0. Okay, 0.29 of a second. So now it's beginning to take some meaningful time. And if we wanted to, well, I wonder if I could stick in an extra 0. I don't want to take the mix too much or make it crash or anything, but let's have a go. So 1 million loops, there we go. And let's watch the time, which is 0.282 seconds. Now, I already know actually that my other example is going to be faster, but I could put more stress on this. For example, this is not like wholly accurate doing t1 minus t0 because you've only run this simulation once. What you might want to do is something like, you could use a time it function, but maybe you could actually put this in a for loop, so for I in range, and then run this operation 10 times to get, and then divided by 10 to get your average. So now the time taken would be this bit. We could run it a number of times, so n times. So number of times. I'll be very explicit here. Times. This is how many times we want to run it. We could say we want to run it 10 times. So number of times, and in order to get the average time taken, we would then have to get the total time, which is these two numbers. I'll put that in brackets, and then divide that by the number of times that we've run our simulation, right? And I haven't, okay, it's not too stressful. Hopefully running it 10 times, if it took 0.282 seconds, it would take 2.82 seconds because that's 10 of those, and the average should hopefully still be around 2.82. But let's have a look and observe just long to check that the code's run properly. So it's doing its thing, and yeah, we do see it looked like it took about 2 seconds as well. And the average, now this is actually the average time taken because we're doing an average over a number of loops, but the average time taken to run 10 of these loops was 0.281 of a second, so about a quarter of a second, basically a quarter or a third of a second. Now that's why Python's deemed to be slow, because generally speaking, if I'm making a loop and for quite a large part of it I might not even be looping anywhere near up to a million, I might even be doing, and this is the convenience of Python, I might be having like my shopping, I would do a shopping list actually, but I couldn't square the numbers, my bill, and I might want to square all of the numbers on my bill, and it'll be a set of numbers, but my bill is not going to be anywhere near a million items. It might be, I don't know, like 10, 50, 100. So this is the convenience of Python. That's what we use it for. But now we want to go for speed because we're trying to do lots of computations per second for whatever reason that we need to do. And if we were to try to do this, so we could make the amount of time a bit more, like put in another 0. We could run this piece of code. Again, we've now done 100 times. Still on average to running it, we'll see, but it's already hanging, and it's going to take probably about 30 seconds now to get there if it does even complete. So we're squaring all of these numbers. We're squaring all of these 1 million numbers that's in our list, and we're doing that 100 times. And we can see that we're beginning to struggle now. Python's got quite slow, but again, the average time taken for the loop. But it's actually the total. Maybe I should actually have the total time taken. Either or. In fact, I will do. I won't even do the average time taken. We'll just do the total time taken. So we won't even divide by the number. But that would have come out at about 30. That was the average time for each of these cycles. But yeah, I don't know. I'm just trying to think. Yeah, you know what? Actually, either or is good. But the point being that it just takes a long time. I'll stick to total time. There we go. So if we did run it again, we'd see something like 30 seconds. In fact, I will run it. We'll see something like 30 seconds on there. Because what's happening is we're iterating over this million item. There's a million items in here, 0, 1, 2, 3, 4, 5, 6, all the way up to a million. We're squaring each one of those, and we're doing that 100 times just for the sake of it, to put pressure on our processor so it's computing harder basically, and it's doing its thinking thing. And I could have even put like a counter in here just to show sort of like the counting, but without the counter it's faster. We see here it's taken 23.9 seconds. Now, how do we get faster? Like, we want to approach other languages. So what do? Well, and this is the trick really, or the thing to do, which is, so I'll comment pretty much. I might keep some of this. We'll keep the time function. I might comment the rest of it out. But the first thing we'll do is we will import NumPy. Oops, how about as NP. So we'll do something like this. We're going to use the NumPy module. Now I have the NumPy module, or at least the docs for NumPy opened over here somewhere. Actually, I was browsing around it myself. So, but it's pretty easy enough to go to where, and you can see like I visited loads of, the number of times I visited this is humongous. But this is a module. NumPy brings computational power of languages like C. So this is actually quite useful to see here because it's already on the front page. It's kind of like telling you this. Brings computational powers of languages like C and Fortran to Python. So the natural list in Python is quite slow. It's slow because it's actually occupying a bit more memory in the way that things are allocated, but it's done for our convenience. But now we want to make this thing faster. NumPy, one of the things that NumPy does is you force all of the elements in the array to be homogeneous items, and it's a contiguous block of memory. That's a humongous part of the speed gain that you're going to get from doing this. So we've imported NumPy as NP, and now we've got to make our NumPy lists. So let's just do that. So I guess we could use, we've got our list there, so I think I'll keep it to say array. We'll make an array equals np dot, and then from that we will do an array. So a NumPy array is what we're going to create. NumPy array. And in order to create the numpy array, we've just got to pass in this object, which is an array type. Well, fantastic, we've got this object already pre-created here. So let's just stick this into our numpy array and we'll try and use that. And by the way, we didn't have to do that. We could create a numpy array even faster. So we never had to create a numpy array out of a list, but just for convenience, it's already there. So we'll put our list in there. Now, one thing that I'm going to do, but I can actually show two things in here, is we will set the d type to equals np.int, and then going to the lowest integer value. Now that's going to occupy less space in the memory. Now, I already know that it's going to throw an error because our numbers go up to 1,000,000 and integer 8 won't house it, so it'll kind of throw an error message, so I'm going to have to increase it. But I'm just going to run it anyway because I think we'd see the error message that comes out of it. But we're now not going to do a list comprehension anymore. How about spelling array right? We're now not going to do a list comprehension anymore, but instead what we're going to do is we're going to square our numbers. And I wonder if I could actually put it straight into this list here. So we're going to comment out this squared list. So we're going to have the same squared list. So squared list equals, and then I believe that we can just do array squared, right? Now we might want to check that that works. So I'm just going to comment this one out. And I might forward it. In fact, what I'll do just to start with is we'll create our squared list before we do anything, just to verify. We'll verify everything, in fact. I'm going to comment everything out here for now. Let's just verify what this array actually looks like, just to start with, to see what we're working with. So we'll run our piece of code. So we're going to now print, instead of printing our list, we're going to print array. F5 to run it. Okay, that's where the errors started to come in, because basically what happens here is int8 will fail in the future. And I actually tried to run this just before and I was like, well, what does that mean? So I pulled it up in Google Bard and basically it just reminded me that, and it's kind of like over here, that the maximum value for int8 is 127, so I can't get away. Like if we wanted to do bigger numbers, we do have to occupy more memory space, but that's fine. We'll go up to int64, which is quite a bit larger, and then hopefully we won't get all of these things scrolling through. So, and they started scrolling through after item number 127, I believe. I don't know if I can scroll back and get to the beginning of it, but that's when they would have started to scroll, that this error message or this warning would have started to flag at that point. So let's just try this again and hopefully that works. So there we go, we get this list. Let's make our list smaller just so that we can observe it. So 1,000, let's just do 1,000 to start with, F5. There we go, we see a nice contiguous list. We're going to expand it to 1,000,000, but it goes from 0 to 999, which is 1,000 elements. So what we're going to do is now make this a little bit bigger because we want to put some pressure on our system here, or test the speed of it. We're not going to print the array now. The reason why we're not going to print the array is because we're going to get an array of 1,000,000 items, and that's going to be quite large. So we're just going to get down to business. So the next thing we're going to do is we're going to do a squared list. Or actually, before I do the 1,000,000, let's just test that our squared list works. So we'll still keep it at 1,000. We'll do our squared list, and then we will do print of the squared list. Now that should be acceptable in terms of size. Let's just run it. F5 to run it. And we get our squared list, and it appeared to work quite fast. But then we noted that our original list worked quite fast for 1,000 numbers. But just to verify that the squared number, it is actually doing squareds. It's probably easiest to see it at the higher elements here. But we've got the same 0, 1, 2. Oh no, that's the original list. Here's our squared list, 0, 1, 4, 9, 16, 25, and so forth. And notice that there was just a slight difference between what a list looks like in the terminal and what a NumPy list looks like. So they look just slightly different, but the reality is we can still see all of the numbers in them. So that's a NumPy list of squared numbers going up to 1000. So you've got 1000 squared, or 999 squared as your top number, just to verify that this number here is actually, if I've got a calculator here, would be 999 times 999, which is exactly that number. So perfect, everything's working so far for the purpose of our test. Well, let's now go and make this bigger. So we put in a million items like this, and now there's going to be no point in printing our squared list because it's going to get too big. And also here for our squared list, we're going to put it inside this loop. So we're not doing a list comprehension anymore, but we will still use this loop. Maybe I could create a new loop. No need to. I'll actually just put it in here. We noted number of times. We're going to get that one as well. So of course that's it. Okay. What we do note, or one thing that we need to note is, we'll start with one time just for our loop, just to get a sake of it, is that we started from T0, we're going to T1, we're measuring the total time taken between T0 and T1. That's what we're going to do. And again, we've got the same roundings, it's all of the same formatting. So we just run this, and we see that this takes 0.007 seconds, so a fraction of the time. And in fact, if I had taken this out of here, so just create our squared list, that'd probably take even less time because we haven't had to construct anything. So be something like this, F5. Oh, so I'm doing the square thing twice here. Let's remove our squared list over here. But anyway, the point being that it's pretty fast. F5, let's run it. So this runs in like 0.003 of a second. So this is very fast, but what we want to do is put a little bit of pressure on it. So we're now going to stick it into our squared list, and we're going to create our squared list, but we're going to now increase the pressure on that. So we're going to say, well, let's do this 10 times. And we've got it up to 1,000,000 as well. So let's see, and remember it took about 25 seconds, something like that, with a regular Python list. So now we're at the same point. We've got this all back, and I will just run it. So F5 on that, we run it. And we see that the total time taken is nowhere near. So we've gone from 28 seconds to less than, well, a part of a fraction of a second. And in fact, I can increase this, to 100 loops. So we've got 100 lots of 1,000,000 squared numbers in here, and run it, and we see that we are still less than a second. So it's doing 100 loops, even compared to 10 loops, was less than 1 second compared to about 23 seconds. So when people do say that Python is a slow language, it consumes lots more processing power, that's not actually true. It's a convenient language that gives you the option to go to something that's fast. And on that note, I guess if anyone's got any comments on that, you're welcome to add your part to it. If you believe any part of it's wrong, or even if you believe that you can do things any faster, that would be even more appreciated. So add that in. Definitely like this video and forward this video on to other people and share it and so forth. And also, just as a note, kind of like it doesn't just work for NumPy. There's a lot of modules that are built off of NumPy, and I'm not sure if that was actually in there if you have it. Well, it was somewhere where I browsed actually to that part of it, but NumPy is used by a lot of other modules. So it's used by like SkyP and Pandas. I think it might even be used by Matplotlib. So it's used by a lot of these other modules, and basically you can be doing the old classical for loops on them, but where you do want to gain speed, you would need to, if you did migrate and if you did cost yourself the time to sort of like construct this NumPy array or make a pandas data frame, you would start gaining the same types of efficiencies, or similarly order of magnitude efficiencies, that you would from the C language, because that's literally what it's leveraging off. So you'll get those advantages basically. And I think that's pretty much it. I'm going to wrap up here. So that's Python. I'll call this. I guess I'll call this video Fast Python. So like, thumbs up, all the rest, follow, and thanks a lot for watching.